This video is dedicated to the wonderful 555 timer chip, an integrated circuit developed in 1971 by an American electronics engineer Hans Kamen-Zinn. Due to its versatility and ease of application, this beautiful tiny device enjoys the well-deserved respect of engineers and hobbyists around the world. It is said that over 1 billion 555 timers are produced annually, making it probably the most popular IC ever made. Today, we will look into internal structure and working principles of the 555. Then we're going to build several typical circuits based on it and analyze their operation. This is Ron Mattino. So, what is the 555 capable of? To answer this question, let's take a look at its block diagram. The first thing that catches our eye is 3 5K resistors connected in series. Contrary to popular belief, it's not them that gave the chip its name. In an interview, Hans Kamen-Zinn mentioned that it was chosen by the marketing department, who thought this name would boost the sales of the product. The resistors, as we can see, are connected between the power pins of the chip, and thus form a classic voltage divider. If, for instance, we power the circuit from a 15-volt source, a voltage of 5 volts will be established across each of the resistors, and the potential at nodes B and A, relative to supply ground, will be 10 and 5 volts respectively. Please note that A is not available for external connection, while B is connected to pin 5 and is named control. This pin is usually connected to an external capacitor that helps filter out power supply noise on comparators, but can be also used to fine-tune voltage divider operation and shift switching threshold. The input stage of the 555 is represented by 2 comparators, whose inputs are wired to nodes A and B of the voltage divider. The principle behind a comparator is fairly simple. It has 2 inputs, positive and negative, also called non-inverting and inverting respectively. A comparator's job is to compare voltages at these inputs. If the potential at the positive input is higher than the negative, the output will be set to logic 1. Otherwise, to logic 0. Please note that comparator inputs take analog levels, while its output is digital, meaning it only switches between 1 and 0. Comparators are commonly used to analyze input signal level. In this case, a certain fixed voltage, which is also called the reference voltage, is applied to one of its inputs, and the signal to be analyzed is fed to the other. As input level exceeds the reference voltage, the comparator will switch its state. Exactly this type of connection is used in the 555. Reference voltages are fed to the comparators from the voltage divider, and if we, again, assume the power supply of 15 volts, 5 volts will be fed to the input of U1 and 10 volts to the input of U2. Please note that the U1 and U2 are connected to the divider with different inputs. U1 uses its positive input, while U2 is connected with the negative one. So, logic 1 will appear at the output of U1 only if the voltage at trig input, which stands for trigger, is below 5 volts, since trig is wired to a negative input. U2 will output logic 1 if the voltage at thresh input, which stands for threshold, is above 10 volts, because thresh is wired to the positive input. So what happens next? Comparators' outputs are fed to the RS flip-flop. RS, also called the SR latch, is actually one of the most basic sequential circuits, whose operation is really straightforward. It has 2 stable states and 2 separate inputs. To switch it to set state, we need to pulse the S input. To reset it, a pulse must be fed to the R input. Please note that, unlike most logic gates, the latch does not simply respond to input levels, but rather retains its state until the next pulse arrives. If, for instance, a short positive pulse is sent to the S input, that's A1 followed by 0, the flip-flop will switch its output to logic 1 and will keep it that way. Similarly, if a pulse arrives at the R input, the RS will switch its output to 0 and remain in the reset state. As we can see, the outputs of our comparators go directly to flip-flop inputs. So, by feeding signal to Trig and Thresh pins, we can switch it. Also take note that the flip-flop in the 555 uses a negative inverting output, which means a 0 will correspond to its set state, while a 1 will correspond to its reset state. Now follow me carefully here. Applying the potential above 2/3 of the supply voltage to the Thresh input will reset the flip-flop. Applying level below 1/3 of the supply voltage to the Trig input will set it. So here's what you must memorize. Trig is activated by low level, but is used to set the latch. Thresh, on the contrary, is activated by high level, but used to reset the latch. So the switching logic is kind of inverted here, but you only gotta remember it once. High level to reset, low level to set. As the diagram shows, this particular latch has an extra inverting reset input wired to pin 4. It can be used to reset the circuit externally. And finally, the output stage. In 555, it is represented by the inverter gate U3 and the transistor switch Q1. If we take a look at full circuit diagram of the 555, we are not going to find a standalone inverter gate here. Instead, we can see a standard push-pull circuit, whose purpose is to output logic 1 and logic 0 levels to pin 3. And the base of the Q1 transistor is simply wired to the input of this circuit. There's no need to dive into details here. All you have to remember is that levels on pin 3 directly correspond to the state of the flip-flop. If it is set, pin 3 will output logical high. If it is reset, pin 3 will output logical low. The IC also has an extra output pin called discharge. It is an open collector output, and if we pull it to the positive power rail with a resistor, it will simply echo levels on pin 3. However, if load is wired between pin 7 and the positive rail, its logic will be inverted relative to pin 3. You can check out my video on transistor switches for that. The link is in the description. You are probably eager to build your first 555-based oscillator. But before we can jump to that, to better understand IC operation, I suggest we experiment with the chip in static mode. We are going to apply permanent levels to its inputs and observe what happens at its outputs. Here is the schematic of our first testing rig. The circuit will be powered by 15 volts. The 555 supports a wide range of supply voltages from 4.5 volts to 16 volts, which, by the way, means you can use it to drive Mosfets. Please note that all inputs of the circuit, except pin 5, do not have internal pull-ups. This means you may not leave any of them floating. So pin 4 must be wired to the positive power rail. As we know already, it is the extra reset input of the flip-flop, which is inverting, hence the connection. Buttons are wired to the Trig and Thresh inputs and use pull-up resistors. Note that Trig is pulled to the positive power rail, and button shorts it to ground. With the Thresh pin, it's the opposite. The button will short it to the positive rail, and the resistor will pull it down to ground. Remember we spoke about different triggering voltage ranges for these inputs? Trig is activated by levels below 5 volts. Thresh is activated by levels above 10 volts. So this connection will work. Initially, both comparators will output zeros. We have 15 volts at the negative input of U1 and 5 volts at the positive input. The negative input of U2 is fed 10 volts, while positive is set to 0. The LEDs are connected to the outputs of the 555. D1 is wired to ground, while the D2 is connected to the positive rail. As usual, we use resistors to limit LED current. Let's see how it works. As I press the buttons, the latch switches. Its state is echoed by the LEDs. D1 is on whenever the flip-flop is set. Remember, pin 3 is a non-inverting output. The D2 state, however, is inverted thanks to the transistor switch that is wired directly to flip-flop output before the U3 inverter. Since both comparators, like I said, output zeros at power on, the initial state of the flip-flop can be random. If we are unhappy with this, we can use pin 4, that's the extra reset input, to zero the latch when power is applied. To do this, connect a capacitor between pin 4 and ground. There is an alternative way to connect the 555 and get the same functionality. Here's what it looks like. The part that's responsible for setting the flip-flop is the same. However, resetting it is now done via pin 4, the reset input. Because we do not need the U2 to reset the flip-flop anymore, the thresh pin is now permanently grounded, which forces the comparator to always output 0. Let's check it out. Looks pretty much the same. However, in this configuration, both buttons close to ground and the pull-ups are connected to the positive power rail. In general, in electronics, pulling up buttons to positive power rail and shorting them to the ground is considered a more proper way of wiring them than the other way around. The reason is that most digital ICs, including microcontrollers, already have internal pull-ups, and if you measure their input voltage, most likely you are going to see a high level. By pulling their input down to the negative rail with a resistor, as we did in our previous example, you risk forcing them into an unstable state, because these two resistors, external and internal, may form a voltage divider. But in the case of the 555, like I said, this is unimportant, since the Trig and Thresh inputs have no internal pull-ups. One way or another, the use of a pull-down resistor in digital circuits should be avoided if possible. The operation mode of the 555 that we have just observed is called BISTABLE, or simply a flip-flop circuit. This means that the device alternates between two stable states and comes from the Latin word bi, which translates as consisting of two parts. The bistable circuit, however, can be implemented in yet another way. We can combine the two inputs, Trig and Thresh, into one. As we already know, Trig is activated by a low level, while Thresh is activated by a high level. So, if we build a voltage divider and apply half the supply voltage to these pins, which is 7.5 volts in our case, this will again force both comparators to output zeros. Now, if we use buttons to pull both the Thresh and Trig to negative or positive power rails, this will also make the latch switch. Let's have a look. There we go. The bistable, in fact, is a pretty simple mode. It's not much different from a regular RS flip-flop, the SN7474 for example. The 555, however, supports a much wider supply voltage range. Also, it has comparators at its outputs, which makes switching smoother and error-free. Mono means one in Latin, so another mode the 555 can run in is called monostable. In this configuration, the IC will have only one stable state, so once the circuit is switched on, it will time once and stop. To start it again, it must be activated manually. The basic connection scheme of a monostable circuit is shown in the diagram. Most of it is already familiar to us. We feed a 0 volts pulse to the trig input using a button connected to the ground, and a pull-up resistor of 4.7 kΩ is used to provide a positive bias when the button is released. As the trig is a setting input, the button will be used to switch the flip-flop into set mode. The reset pin is hardwired to positive rail. We do not need it in this configuration. However, thresh and discharge pins wiring is different. They are now connected together, along with the C1 capacitor, which is wired to ground, and the R2 resistor connected to the positive rail. So, how does the monostable circuit work? Initially, 5 volts from the R1 resistor is fed to the lower comparator's negative input through the trig pin. That makes the U1 comparator output 0. The RS flip-flop is reset, which makes its inverting output 1, and the transistor switch is on. This shorts the C1 capacitor to the ground, preventing it from charging. Because 0 volts is fed to the thresh pin from the discharge pin, the upper comparator also outputs 0. The LED is also off, because pin 3 is low. Now the user briefly presses the S1 button. 0 volts arrives to pin 2, which makes the bottom comparator output logic 1 and switch the flip-flop into the set state. The LED illuminates. At the same time, the transistor switch turns off. This allows the C1 to start charging through the R2 resistor. The voltage at the thresh pin starts to rise. As it reaches 2/3 of the power supply voltage, which is the switching threshold for the upper comparator, a logic 1 is fed to the R input of the latch, making it reset. The LED turns off, the Q1 switch turns on. Now the system is back to its initial stable state. Let's see how it works. And it looks like we've just come up with a simplistic timing circuit. The delay time here will be approximately 1 second. We can observe the rise of voltage on the capacitor using a scope. As we can see, the cap charges gradually and discharges instantly. This is due to the transistor shorting it to ground. So the Q1 in this circuit, therefore, performs the function of discharging the capacitor. That is the reason why pin 7 of the 555 is called discharge. The formula for calculating timer delay is quite simple. T equals 1.1 times R times C, where R is the resistance in ohms and C is the capacitance in farads. It is easy to calculate that 1 microfarad and 1 megohm will provide us with a delay of about 1 second. To increase it, you have to either use a larger resistor or a larger capacitor. In circuit design, priority is usually given to increasing the resistance, since using large capacitors may impact the size and cost of the final product. Let us use a 5 megohm resistor. Isn't that beautiful? Done. And the capacitor again discharges instantly, and the LED turns off. It's important to realize that it's not possible to increase resistance indefinitely. That could result in really low charging currents, comparable to the leakage currents of the capacitor. As a result, the cap will simply never charge. Mastering choice of correct values and ratings usually comes with experience. You may have noticed that we never used pin 5 in any of our circuits. It's the control input, which is wired to the top node of the 555 voltage divider. The purpose of this pin is connection of a small capacitor, whose task is to smooth out the ripple of the power supply. A comparator is a very sensitive device, and even insignificant power disturbances can affect its operation. So, in a final product, the capacitor at pin 5 is essential. Since we use a lab power supply in this video, filtering is not exactly necessary. And by the way, if you're interested in purchasing the DPS 5020, that's the power supply I use in my videos, I will leave a link to it in the description. The circuit that we have just assembled is also called a monostable, or one-shot multivibrator. A monostable produces a single output pulse of a certain duration when triggered externally. Why would we need such a device? Guess what this is? It's a fan rotation detection circuit. While pulses are being received from the fan's Hall effect sensor, the red LED is lit, indicating that the fan is working. As soon as the rotor stops, for example, the motor fails or an object gets into the propeller, the indicator goes out. And finally, we've gotten to the last part of our video, which describes perhaps the most common use of the 555 timer. The circuit shown in this diagram is called the ASTABLE oscillator, or ASTABLE multivibrator. For the sake of clarity, we will set up the ASTABLE to generate low-frequency pulses and observe the LED flash on its output. The first thing that catches our eye in this schematic are the Trig and Thresh inputs wired together, meaning they receive the same signal. So what's going to happen here? When the circuit is powered on, the C1 capacitor is discharged, and 0 volts is applied to both inputs. This makes the top comparator output logic 0. The bottom comparator, however, will output logic 1. This will make the flip-flop switch to the set state. Remember, the output is inverted. Due to this, the transistor switch, whose collector is connected to the discharge pin, will be off. So the C1 capacitor will start charging thanks to the positive bias coming from resistors R1 and R2 connected in series. The charging speed of the capacitor will depend, firstly, on its value, and secondly, on the value of these resistors. As soon as the voltage at the Thresh input reaches the 2/3 of the supply, which is 10 volts in our case, the latch will reset. This will produce a logic 1 on its output. The transistor will switch on and pull the discharge pin to the ground. Capacitor C1 will now start discharging through the R2 resistor. As its voltage drops below 1/3 of the supply, that's 5 volts, the lower comparator will respond and output a logic 1. The flip-flop will set, and the transistor switch will turn off. This will bring the circuit to its initial state, and the C1 will once again start charging. As a result, oscillations will set in. This circuit, in fact, is nothing more than a typical case of a feedback loop. The signal is simply passed from the output to the input of the IC. However, due to the presence of an RC circuit formed with R2 and C1, the transition between on and off states is not instant, which means the frequency and the duty cycle of our oscillator will be determined by the values of C1, R1, and R2. Because the capacitor is charged through both resistors, but discharged only through the R2, if we want to get waveform close to meander, the resistance of R1 must be relatively low compared to resistance of R2. And if you need to know exact duration of positive and negative parts of the waveform, you can use formulas shown on the screen. Looks like our oscillator is running. However, duty cycle is obviously pretty far from 50%, the meander. Why? The reason is because the capacitor charges through both the resistors, while it's discharged only through the R2, so the charge and the discharge currents are slightly different. How can we make duty cycle adjustment more accurate? Obviously, we must separate the charging and discharging paths from each other. To achieve this, we need to introduce a couple of diodes into our circuit. This time, the capacitor will charge through R1, D2 and R3, while the D1 will remain reverse biased. When the transistor switch turns on and 0 volts sets on pin 7, D2 will become reverse biased and the discharge current will pass through D1 and R2. As the total resistance of R3 and R1 is equal to the resistance of R2, and the diodes obviously provide the same voltage drop, currents flowing over charge and discharge paths will be identical. Thus, the time high and the time low of the oscillating cycle will be balanced. As we can see, the duty cycle has now approached 50%. We can, in fact, come up with an even simpler circuit here. We need the R1 resistor because the discharge pin is an open collector output, which means it needs a pull-up resistor to operate. However, if we use pin 3, which is, remember, a push-pull output, to drive the capacitor, we can drop the extra resistor. Our revised circuit will now look like this. And we can use the discharge output to drive external load, the LED in our case. In ASTABLE mode, the 555 timer can also be used as a pulse width modulation PWM-controller. To achieve this, all we need to do is increase oscillation frequency by reducing the value of the C1 capacitor and replacing the R2-R3 stage with a potentiometer. We are also going to need a capacitor at pin 5 here. It is necessary to suppress high-frequency noise which may affect the comparators. So here comes our PWM. We can observe how the LED intensity changes in accordance with the duty cycle. As I turn the potentiometer, the output frequency, however, also changes. This is obviously due to change in resistance, which affects the parameters of the RC circuit responsible for the switching delay in the feedback loop. Let us now go back to our previous configuration and use the discharge output to drive the capacitor, while the LED will be wired to pin 3. And it looks like our circuit is not working correctly. As the potentiometer is turned, the LED brightness first starts to drop, but then rises again. The scope shows that we have some sort of parasite oscillation at the output. Let us try to lower supply voltage to 9 volts. Looks like everything's working fine now. And the oscillation is more stable too. Let us measure it with a multimeter. The meander frequency is about 300 Hz. As I increase the duty cycle to about 80%, it goes down to some 280 Hz. Not too bad. Let us try to lower the duty cycle. It's 360 Hz now. So, once again, why does the frequency change? For the same reason. Charging and discharging currents of the capacitor flow through different paths. The C1 is charged through R2, D1 and R1, and discharged through D2 and R1. This problem is also quite easy to solve in this configuration. All we need to do to balance currents is add a single resistor to the circuit. Can you guess where it should be placed? You can pause the video and take a moment to think. What's going to happen now? Charging current will flow over the same path, but the discharge current will now go through an additional R3 resistor, which will compensate for the R2. Naturally, the values of R3 and R2 must be the same. Okay, now let us see how it works. The frequency is now about 280 Hz. Let us increase the duty cycle. Looks like the frequency has not changed much. Let's see how we're doing on the low end. It's obviously also better, but not quite as desired. Looks like frequency instability here is due to the time-low duration of the cycle changing disproportionately compared to time-high duration as duty cycle is adjusted, which means the time during which the latch is in the reset state is slightly out of balance with the time it is set. As you remember, it's the upper comparator that is responsible for resetting the latch. Incidentally, the control pin is wired directly to it. So, we can try to shift the threshold level of this comparator by pulling pin 5 down to the ground with a resistor. By trial and error, I came up with a value of 21 kiloohms. Let's see what we got now. Actually, it's pretty good. Let us turn up the power supply to 15 volts. Everything is fine here now too. The magic resistor at the control pin solved everything. I think it's obvious now that the 555 timer cannot boast great stability. But that's really not what we expect from it. In PWM circuits used to drive high current loads, maintaining constant frequency is not that critical. Let us take a look at a small circuit that can be used to drive any resistive load powered from an AC source, like an incandescent lamp, a heater, or a DC electric motor. The 555 configuration is quite typical here. The PWM signal produced at pin 3 is fed to a Mosfet driving the load. The circuit, as you can see, is transformerless, which means the load is powered by voltage rectified using a diode bridge, and the 555 is powered by a simple step-down circuit made of an 18 kiloohms 5 watts damping resistor and a 12 volts Zener diode. Last but not least, you probably noticed that all circuits shown today have two capacitors wired in parallel with the power supply. Why two? Why not use a single cap of equivalent capacity? The reason is they serve different purposes. The 10 nanofarads is there to suppress parasiting self-oscillation at high frequencies. The 47 microfarads supplies power to the circuit at switch times. What does that mean? In a typical scenario when the circuit contains load, which is just an LED in our case, but could be anything, whenever the latch switches, power supply voltage may change. Although these voltage fluctuations are really minor, they can disturb the comparators by affecting their switching threshold, and thus cause many undesired effects. So the 47 microfarad capacitor helps maintain load changes. In real designs, the 10 nanofarad capacitor is often soldered directly to the power pins of the IC, or right next to it. The electrolytic capacitor is usually connected directly to power rails, where the maximum number of connections of the rest of the circuit is accumulated. As a final note, there is also a CMOS version of the NE555 called the LMC555. It can boast better stability, higher frequency range, 3 MHz versus 500 kHz, much lower power dissipation and supply current spikes, and a minimum supply voltage of 1.5 volts compared to 4.5 volts of the original version. Also, at 5 volts supply, output is fully compatible with TDL and CMOS logic. So, if you can get your hands on the LMC555, it's definitely worth your attention. Either way, The 555 does an excellent job overall, and its low cost makes it perhaps the easiest and most affordable solution for implementing pulse width modulation functionality. However, if your application requires high accuracy and stability, you should definitely look into microcontrollers. Or, if you are building an LED driver, there's a bunch of dedicated LED PWM-controller ICs that will do their job better than the 555. And that's it for today. If you found this video useful, please do not hesitate to give me a thumbs up, share it in social media, and, of course, subscribe to this channel. If you are interested in purchasing components or equipment shown in the video, you can find the links in the description. Or, if you really would like to support the channel, you can go with YouTube's subscription. Members get access to exclusive content, including all diagrams in JPEG format, Arduino sketch source code, and full plain text transcripts of all videos found in this channel. To become a member, please follow the link found in the description, or simply press the join button. This was Mattino. See you next week.